Now the next chapter, that is moving charges and magnetism. Chapter number 4. Okay. See, in standard 11th, we discussed in first chapter, initially electricity and magnetism, these two branches were developed independently. But then after scientists observed this thing, electricity and magnetism, that is inseparable. So in this particular chapter, we will discuss about the dependence of electricity and magnetism on each other. Okay. Say, scientist Oersted experimentally observed this thing. When the current flows through any conductor, the magnetic field is produced in the surrounding of it. In one of his experiments, he observed this thing: when the current is passed through the conductor, then the magnetic needle placed nearby to it is deflected, and noticeable deflection is observed in it. So with the help of large number of repetitive experiments, finally he concluded this thing: whenever the current flows through any conductor or current is passed through any conductor, the magnetic field is produced in the surrounding of it. So Oersted noticed that current in a straight wire caused a noticeable deflection in the nearby magnetic compass needle, which suggests this thing: the magnetic field is produced, because magnetic needle always align in the direction of Earth's magnetic field. And when it shows the deflection, it implies that definitely some other magnetic field is there, and it is under the effect of some other magnetic field. So, with the help of experiments, he observed this thing: if the current passed through the conductor, which one is placed perpendicular to the plane of paper, now current is in outward direction, this first figure. So if the current is in outward direction from the plane of the paper, then it is represented by the dot in a circle. And if the direction of the current is going inside, perpendicular to the plane of paper, then it is represented by cross. Then he observed this thing: if in the surrounding of this current carrying conductor the iron dust is sprinkled, then it is arranged in the circular form. So one can say this thing now: the magnetic field is produced in the surrounding of the current carrying conductor in the circular form. Okay. And at different positions, by placing the magnetic needle, he observed this thing: if the current through the conductor is in outward direction from the plane of the paper, then the magnetic field produced in the surrounding of it, that is in anti-clockwise direction. And if the current through the conductor is going inside, perpendicular to the plane of paper, then in the surrounding of it, the magnetic field produced, that is in clockwise direction. So Oersted concluded that moving charges or currents produces a magnetic field in the surrounding space. Clear up to this one? Now here one can take the idea about the magnetic field produced by the current carrying conductor with the help of right hand thumb rule. Suppose this one is the conductor, then we have to hold it in the right hand, as you see, in such a way that thumb that should be in the direction of the current. Now, if the thumb is in the direction of the current, then the fingers enveloping to this conductor represent the direction of the magnetic field enveloping to this conductor. Okay, so one can fix the direction of the magnetic field using right hand thumb rule. So magnetic field that is in the circular form. So here at any point, if we draw the tangent to that loop, then it will give you the direction of the magnetic field at that particular point. Clear to all of you? Now the next topic, that is sources and fields. Now see, in chapter number 1, we discussed this thing, the electric charge Q, that is the source of electric field. Why we say this? Because electric charge, which is represented by Q, that produces the electric field E. And we know this thing, this electric field at any point, which one is at distance r from the charge Q, that is given by the equation E, that is kq upon r square into r caret, where r caret is the unit vector in the direction of electric field at that point. K, this constant, that is 1 upon 4 pi epsilon 0, where epsilon 0, that is the permittivity of free space. And we already discussed this thing. If any other charge Q is placed in this electric field E, then it experiences the force. And the force acts on charge Q placed in electric field E, that is given by Q into E. So we can write the force acting on charge small q in the electric field of charge capital Q, that is 1 upon 4 pi epsilon 0 small q capital Q upon r square into r caret. We already studied this thing. Now, just as static charge produces the electric field, the moving charge, that is nothing but electric current. That moving charge produces the magnetic field. And here some basic properties of electric field and magnetic field are identical. Later on we will discuss this thing. And just like electric field in the space, at each and every point, the magnetic field can be defined. And like electric field, magnetic field is also the vector field. And here, like electric field, we can use the superposition principle for magnetic field also. Say, if we have discrete distribution of charges, or we have more than one electric fields at any point due to different charges, then to find out the resultant electric field at that particular point, what we do? We take the vector summation of the electric field due to each and every individual charge. And then we find the resultant electric field. And that is the superposition principle. Exactly like that. For different current, if we want to find the magnetic field at a particular point in the space, then we have to take the magnetic field at that particular point due to each and every current, and then after, by taking the vector summation of all those magnetic fields due to individual currents, we can find the resultant magnetic field at that particular point. Clear to all of you? Now, next topic, that is magnetic field, Lorentz force. Now, see, we already discussed this thing. When any static charge is in the electric field E, the force acts on it, that is Q into E. So, we can write the electric force on charge Q in the electric field E, that is Q into E. Similarly, when any charge Q is moving in the magnetic field, the force acts on it. And that particular force, that is called magnetic force. So if any charge Q is moving in the magnetic field B with velocity V, then the magnetic force act on it. That is given by the equation F magnetic, or we can write Fm, that is Q into V cross B. So here the magnetic force that is represented by equation Q into V cross B means we can understand this thing here. The direction of the magnetic force on the moving charge, that will be perpendicular to both the velocity and magnetic field. And we can fix the direction of the magnetic force with the help of right hand screw rule. Say, electric force that is always in the direction of electric field. Okay, because F, that is Q into EQ, that is scalar quantity. So whatever is the direction of electric field, that will be the force on charge Q. Clear? And if the charge is negative, then the force that will be in the opposite direction of the electric field. But here one can fix the direction of the magnetic force by the right hand screw rule or right hand thumb rule with the help of this vector product. Clear to all of you? Now, if electric field and magnetic field both are present and the electric charge is moving in these fields, at that time the resultant force acting on it, that is equal to the vector summation of electric force and magnetic force. So we can write the resultant force F, that is electric force, that is Q into E, plus magnetic force, that is Q into V cross B. So resultantly we can write the resultant force on the electric charge QF, that is Q into E plus V cross B. And this particular resultant force on the charge Q in the presence of electric and magnetic field both, that is called Lorentz force. That is called Lorentz force. Clear? We already discussed this thing. When any charge Q is moving in the magnetic field B with velocity V, then the magnetic force on it, that is given by Q into V cross B. We also discussed this thing, the direction of this resultant force, that is in the direction perpendicular to both V and B. If we think about the magnitude of this particular force, then we can write the magnitude of magnetic force, that is QVB sine theta, where theta is the angle between V and B. Now here we can discuss some special cases. Suppose the charge is moving with velocity V in the direction of magnetic field. So if velocity is in the direction of the magnetic field, it implies that V and B both are parallel. So theta, that is 0. In that case, we can write here sine theta, that is sine 0, sine 0, 0. So magnetic force will be 0. Or if the charge q is moving with velocity v in the opposite direction of magnetic field. So if v and b are antiparallel, then the angle between v and b, that will be pi. Okay, so sine theta, that is sine pi, again it is 0. So here we can conclude like this: if the velocity of the charged particle is along the direction of the magnetic field, either in the direction of the field or in the opposite direction of the field, the magnetic force acting on it, that will be equal to 0. Clear? Now let's derive the unit of magnetic field B. Say, from this equation of the magnitude of magnetic force on charge Q, we can write B, that is equal to Fm upon QV sine theta. Now unit of B, that is equal to unit of force, that is Newton, upon unit of charge q, that is coulomb, and of v, velocity, that is meter per second. So that second is written here in numerator. Now this Newton second upon coulomb meter, that is called Tesla on behalf of the name of scientist. This unit is called Tesla. Okay, so we can say Tesla, that is the SI unit of magnetic field B. Its small unit, it is non-SI unit, that is called Gauss. And one Gauss, that is 10 raised to minus 4 Tesla. Now from this unit, you can prepare the dimensional formula also. Say, dimensional formula of magnetic field B, that is equal to dimensional formula for force, means of Newton, that is M1 L1 T minus 2. For second, T1. For Coulomb, means for charge Q, A1 T1. And for meter, you can write L1. So this T1, T1 cancelled. This L1, L1 cancelled. So finally you will get M1 L0 T minus 2 A minus 1. That is the dimensional formula of magnetic field B. Clear? Now see, we already discussed this thing. When any charge q is moving in the magnetic field, the force acts on it. So we can understand this thing: if any current carrying conductor is placed in the magnetic field, then it will experience the force, because after all, in the current carrying conductor, the charges are in motion. So when any current carrying conductor is placed in the magnetic field, it implies that the moving charges are in the magnetic field. Now here, suppose as shown in the figure, we have uniform magnetic field in which a conductor having length L is placed. Which one is connected with the battery? Now when the circuit is switched on, suppose current I is flowing through this particular conductor in the direction as shown in the figure. And now we have to derive the equation for the force acting on this current carrying conductor. Clear?
Yes, sir.
Now, suppose here the number density of charge carriers in this conductor, that is small n. Number density means the number of charge carriers per unit volume, that is equal to n. Now here length of the conductor is L and its cross-sectional area, that is suppose A. Then the total volume of the conductor, that we can write A into L. Now per unit volume, the number of charge carriers, that is N. Therefore, in total volume AL, the number of charge carriers will be how much? So we can write, therefore, the total number of charge carriers in the given conductor, that is NaL. Okay. Now, if here in the conductor I current is constituted due to flow of those charges, and here the charges are moving with drift velocity. So we can write the magnetic force on total q amount of charge which are moving with velocity Vd, which are constituting the current I in the conductor. That is q into Vd cross B. Now, this total q amount of charge, that is how much? So we already calculated the total number of charge carriers in the conductor. So total number of charge carriers, that is NaL, and these charge carriers are electrons. So per charge carrier, the charge is E. So total amount of charge flowing through any cross section of the conductor, that is NaLe, which one is constituting the current I in the conductor. So replace Q by NaLe. Okay. Now we have the equation J, that is the current density, equal to NEVD. So we can replace this NEVD by current density J. So we can write the equation for the magnetic force, that is equal to A L J cross B. Okay. But A into J, that is current I, because current density J, that is equal to I upon A. So we can replace this A into J by I. So we can write the magnetic force, that is IL cross B. Here IL, or suppose in some cases we consider infinitesimal small line element of the conductor. Then we can write IDL. So this product of I and L or IDL, that is called current element. That is called current element. And here when we consider the current element, at that time we have to take care about this thing. We have to consider the line element or the length of the conductor that is perfectly parallel to the direction of the flow of current. Okay, so here see, you can observe one thing. When this A and J, A into J, that is replaced by I is the scalar quantity. At that time, the vector sign that is placed on L. Because the direction in which the current is flowing, in that particular direction, we define the current density. And when we take the current element in the direction of the flow of current, it implies that L and J both are in the same direction. So when L and J both are in the same direction, then in that case, if you place the sign of the vector on J or L, it represents the same thing. Clear? So here now resultantly, we can say this thing: when any conductor having length L carrying current I is placed in the magnetic field B, the force acts on it, that is IL cross B. And the direction of this force, that is perpendicular to both IL and B, and the direction of this resultant force, that can be fixed with the help of right-handed screw rule. Clear? Now, if the current carrying conductor is not the straight one, suppose the current carrying conductor that is as shown in the figure. Now this particular conductor or the wire is carrying current I. So in this particular case, what we have to do? We have to divide this particular conductor, or in other words, we can say the entire length of the conductor into so many infinitesimal small line elements. And when we consider infinitesimal small line element, then we can prepare the current elements as IDL1, IDL2, IDL3, IDL4 up to IDLn. Why we divide this one into so many infinitesimal small line elements? Because when we prepare the current element at that time, we have to take current and the line element both parallel to each other. And for this type of curved conductor, we have to take infinitesimal small line elements. Now, here, suppose the line elements are DL1, DL2, DL3 up to DLn. Corresponding to it, we prepare the current elements IDL1, IDL2, IDL3 up to IDLn. Now, the forces on these current elements that we can write F1, that is equal to IDL1 cross B, that is the force on the first current element. F2, that is IDL2 cross B, that is the force on the second current element. Up to Fn, that is equal to IDLn cross B, that is the force on nth element. So in this way, first of all, we have to calculate the force acting on each and every current element, and then after take the vector summation of all these, we will get the resultant force acting on that current carrying conductor. So we can write the resultant force F, that is equal to sigma I equal to 1 to n I dli cross B. And this summation that we can represent by integration also. Here I, that is constant throughout the conductor. So we can write resultant force F, that is equal to I integration dl cross B, and this integration should be carried out over this line of the conductor. Clear to all of you? Example 4.1. A straight wire of mass 200 gram and length 1.5 meter carries a current of 2 ampere. It is suspended in mid-air by a uniform horizontal magnetic field B. What is the magnitude of the magnetic field? Now, see here, mass of the wire, that is 200 gram, that is 0.2 kilogram, that is given to you. Length of the wire, that is 1.5 meter, and 2 ampere current is passed through it. Now we know this thing, the weight of this conductor or wire, that is in downward direction, that is equal to mg, and under the effect of this particular force, it will move in downward direction. But now we want to suspend it in mid-air. So we can understand this thing. This downward force mg, that must be balanced by some other force which is in opposite direction to it. So we know this thing, when any conductor is placed in magnetic field B, and if current I is flowing through it, then the magnetic force act on it, that is ILB sine theta. Now see here, your current carrying conductor, that is in the plane of paper. And see, the magnetic field is represented by the symbol of cross in the circle, which represent this thing. The magnetic field is perpendicular to the plane of paper going inside. It implies that theta, that is 90. So we can say the magnetic force on the conductor, that is ILB. Now, this ILB, that is in upward direction, as per right hand screw rule, you can check if the magnetic field is going inside, and current, that is as shown in the figure, in right side direction in the plane of the paper. Then as per IL cross B, the force act on it, that is in upward direction. Now see, mg downward, magnetic force upward. So these two forces are acting on the conductor, and these two are in mutually opposite direction. So if these two are equal in magnitude, then the net force on the conductor becomes zero, and it will remain suspended in mid-air. So we have to take magnitude of both the forces ILB, that is equal to mg, right? Magnitude of both the forces, that is same one. Now make B as a subject. So B, that is mg upon IL. So M, that is 0.2 given to you, G, that is 9.8. Current I through the conductor 2 ampere given to you. Length of the conductor, that is 1.5 meter. Solve this one, you will get the answer, magnitude of the required field. Clear? Now example 4.2. If the magnetic field is parallel to the positive y-axis and the charged particle is moving along the positive x-axis, see the figure. Which way would the Lorentz force be for A, an electron, that is negative charge, and B, a proton, that is positive charge? Now see here, magnetic field given to you that is in y direction, and velocity of electron and proton both that is given to you in positive x direction. Now see, the force on proton, so that is equal to Q into V cross B, as per that Q that is charge E of proton, velocity V that is VI caret because velocity that is in positive x direction, magnetic field that is in positive y direction, so that is Bj caret. So we can write that is equal to EVB into I cross J. In standard 11th, we studied this thing, I cross J that is equal to K caret. So force on proton that is EVB K caret. It implies that we can say the force on proton that is in positive Z direction. Clear? Now force on electron. So for electron charge that is minus E, velocity that is in positive x direction, B that is constant one. So we can write the force on electron that is minus EVB K caret. So we can say this thing, the force on electron that is in negative Z direction. Clear to all of you?